Hi, my name is Emily Moody, and my topic today is tritium degradation. So what is tritium? Well, hydrogen has three isotopes. The first one is protium. It's the most common and the most abundant isotope. It has one proton. The second isotope is deuterium. It's also known as heavy hydrogen. It has one proton and one neutron and naturally occurs in the ocean. The third isotope is called tritium. It has one proton and two neutrons. It goes through beta decay and has a half-life of 12.32 years. Hydrogen and its isotopes react with almost every element on the periodic table because of their unfilled electron shell. It's very mobile because of its small size, resulting in various types of damage. According to the ASM Materials Handbook, there are 5 types of hydrogen-induced damage. The first is hydrogen-induced blistering. Then we have cracking from precipitation of internal hydrogen. Next is hydrogen attack, cracking from hydride formation, and hydrogen embrittlement. Again, because hydrogen is so small, with its one proton, it can easily migrate through the crystal structure of most metals and alloys. It migrates by dissolving into a metal as a hydrogen atom, called nascent hydrogen. The dark region shown here is uniform tritium penetration in an elastically strained region of stainless steel. Hydrogen absorbed into the metal can be found at one of two locations in the microstructure, either interstitial sites in the lattice or extraordinary sites that are associated with crystalline defects. Interstitial sites are empty spaces or gaps in a material's lattice. Hydrogen atoms in interstitial sites are called dissolved hydrogen. Because nascent hydrogen is larger than the interstitial sites, they expand the lattice. This causes the hydrogen to want to be at the extraordinary sites because it fits more easily. Extraordinary sites are sites where the lattice is already expanded, and they include grain boundaries, vacancies, and dislocations. Hydrogen at these sites is called trapped hydrogen. Once these sites are filled, hydrogen continues to permeate through the rest of the metal. As the temperature increases, so does the activity. Hydrogen-induced blistering is the first form of hydrogen damage that we're going to talk about. In blistering, nascent hydrogen atoms accumulate at the extraordinary sites. It includes interfaces between inclusions and the metallic matrix and laminations. As hydrogen accumulates, nascent hydrogen atoms recombine to form hydrogen molecules which exert a high pressure on the interface. This pressure can be enough to plastically deform metal by rupturing interatomic bonds and forming microscopic voids and microscopic blisters. The process will depend on the concentration of hydrogen, the trapped to dissolved hydrogen ratio, and the temperature. The formation of the blister depends on whether metal has inclusions or other internal surfaces where hydrogen can accumulate. It also depends on the metal absorbing enough hydrogen to create enough pressure. To mitigate blistering, metals and alloys should be kept clean to avoid internal surfaces. Processes that minimize hydrogen absorption should be used. Components should be heated after processing to remove the hydrogen. Inhibitors can be used that minimize exposed surface corrosion, or metals and alloys with low hydrogen permeation and low tendency for hydrogen accumulation can be used. Shown here is the initiation of a hydrogen-induced blister in 1020 steel. The picture on the left is at 200 times magnification, and the picture on the right is at 3,000 times magnification. Cracking from precipitation of internal hydrogen. This cracking from internal hydrogen involves hydrogen absorbed at high temperatures from moisture in the atmosphere. Areas around inclusions, precipitates, and laminations can be embrittled by supersaturated hydrogen as the temperature drops during forging, welding, and casting. As the molten metal solidifies, the solubility of hydrogen is decreased significantly, and hydrogen accumulates at voids, pores, and internal surfaces. As the pressure increases, stresses at the tip of the void also increase. High-pressure hydrogen at surfaces causes defects to extend in a brittle way. As the crack extends, hydrogen pressure decreases, slowing the crack growth. Shown here are surface cracks on tensile specimen strained in the presence of high-pressure hydrogen. Picture A is just in air and uncoated. Picture B is uncoated at 10,000 psi hydrogen. Picture C is titanium coated at 10,000 psi hydrogen. And picture D is also titanium coated, but was strained in 0.3% hydrogen before the titanium coating was applied, and then was exposed to 10,000 psi hydrogen. As hydrogen atoms accumulate to form hydrogen molecules in these areas, localized brittle ruptures or cracks called fisheyes, shatter cracks, or flakes are formed in the structure. This is an example of a fisheye fracture on the surface of 4140 steel after a tensile test. The intergranular fracture process results in a semi-flat surface that appears shiny, called the eye. And here are some examples. The surface conditions of the void where the hydrogen originally accumulated may provide the pupil for the eye. Fisheye doesn't form until the specimen is in tension because hydrogen-induced crack growth needs stresses close to the yield strength of the material at the void tip. This results in specimen passing non-destructive inspections, but then failing once placed in service. To mitigate this, molten metal should be protected from moisture. If hydrogen is already present in the specimen, heating the component slightly above room temperature can release the hydrogen from the material. The H samples shown on the right were heated to 260 degrees Celsius for 1 hour to remove the hydrogen. Shatter cracks are the result of a combination of stresses, flow lines, and hydrogen content causing multidirectional cracking. They are formed because of hydrogen gas precipitating in micropores or precipitating along the inclusions at metal interfaces. They are also formed because the presence of the hydrogen at the metal surface promotes crack extension by macroscopically brittle processes, or because of tensile stresses being high enough to cause crack extension. The term shatter crack originates from multidirectional cracks observed in a material that had been forged and were thought to be the result of shattering from forging hammers. This shows a hydrogen flake approximately 2 inches in diameter at the center of the fracture surface. It is a crack caused by hydrogen precipitation at voids and interfaces due to processing-induced stresses. It's similar to the development of fisheyes, but formed in forging or rolling instead of tensile testing. It forms during the cooling to room temperatures because of residual stresses produced by plastic deformation. Hydrogen attack happens when hydrogen interacts with carbides to form steam, for example, when interacting with copper oxide inclusions in copper alloys. This picture shows copper that was annealed in hydrogen in order to maintain the bright surface free of oxide. Cavities were formed near the copper oxide particles in grain boundaries, and this picture is shown at 500 times magnification. Hydrogen reduces copper oxide, producing water and copper, making it prone to hydrogen attack. This occurs in copper or copper alloys containing oxygen and copper oxide inclusions. When this occurs at the critical temperature of water, the copper inclusion, usually at the grain boundaries, is replaced with steam. This results in a steam pocket or bubble, which forces the grain apart and eventually causes grain boundary fracture. Because of the ability to produce oxygen-free copper in industry, it is not a very prevalent occurrence. However, this also happens in oxygen-containing silver alloys and in steel. Hydrogen attack also occurs in steel when hydrogen interacts with carbides to form methane. The process of decarburization will begin immediately after steel is exposed to high hydrogen pressures and high temps, causing surface reactions between the carbon and the steel and the hydrogen in the environment, resulting in the production of methane. If the process continues, the carbide content in the surface region will be reduced to the point that carbides will begin to dissociate. This will lower the strength and ductility of the steel and allow hydrogen to be absorbed. The hydrogen will accumulate at pores and micropores at grain boundary inclusions or other defects. Within the pores, nascent hydrogen will recombine into hydrogen molecules that then react with the carbon to form methane by the same reaction that caused surface decarburization. The methane will stay in the micropores caused by the removal of the carbides. As the concentration of methane increases, so does the pressure. Either equilibrium will be reached or the pressure will expand the micropore. The equilibrium methane pressure is dependent on the stability of the carbides, so to mitigate the potential of hydrogen attack by reducing the methane pressure, strong carbide formers should be alloyed with the steel. However, if the pressure expands the micropore, the growth will lead to the combining of microcavities and microcracks to form an intergranular crack that may potentially rupture, as shown. When hydrogen content in rare earth metals, for example titanium or uranium, is greater than the solubility limit, metal hydrides precipitate and will reduce the ductility of the alloy. This is achieved by very small hydride sites that can begin and more easily combine microvoids. When the stress concentration at the crack tip is sufficient, plastic strain and crack orientation may significantly reduce the ductility of the alloy. Also, when a material containing hydrogen is placed in service, is subjected to stress and temperature changes, this will cause the hydrogen to be redistributed. Hydrogen will accumulate at areas of high dilational stresses and eventually precipitate as a hydride, which will fracture and relieve stresses that act on the hydride. The stresses will then be concentrated at the newly formed crack tip, and hydrogen will migrate to another stress region, repeating the process. This will occur until the crack reaches a critical size and the component fractures or the stresses are relieved. In this picture, hydrides located beneath the gauge mark have an obviously different orientation than the random hydrides away from the mark. This is due to the dissolution and reprecipitation of hydrides. The effect of hydride formation on mechanical properties depends on the orientation and distribution in the component. Hydride platelets will be arranged perpendicular to any tensile stresses, and they will tend to cluster so that rows or columns of platelets are formed. Because of the reduced ductility, the hydrides and hydride metal interfaces create a nearly effortless path for crack propagation along the hydride column and across the material. This shows the stress orientation of hydrides in Zircaloy 2. A is stressed and B is non-stressed. Hydrogen embrittlement occurs when hydrogen is induced during manufacture or service and follows the same process as hydrides. Because the absorbed hydrogen atom is too large for the interstitial site in the metal lattice, it will migrate to the extraordinary site where the lattice is dilated. Because the extraordinary sites are randomly distributed in the material in a component that is unstressed, the hydrogen is also randomly distributed. However, when the component is placed in service, localized stresses will result in lattice dilation. Hydrogen will then migrate to these areas, increasing the local hydrogen concentration. Depending on the metal and the temperature, when hydrogen concentration reaches a critical amount, a crack will occur. As the crack propagates, the region of high stress and lattice dilation will move to an area below the new crack tip. Hydrogen will relocate to this new dilation area, and the process will repeat until component failure or the load on the component is reduced so that critical hydrogen concentration is not reached in the area of lattice dilation. This process lowers the strength of the metal alloy interfaces. Shown here is an autoradiograph of tritium segregation to the grain boundaries in iron. Helium-3 is a product of radioactive beta decay of tritium. It is a non-radioactive isotope of helium with 2 protons and 1 neutron, making it larger than tritium. During beta decay, conservation of energy and momentum dictate that the daughter nucleus takes some of the momentum with it. When a tritium atom goes through beta decay, the recoil energy is carried away by the helium-3 ion. The decay of tritium that is already in a metal produces no lattice damage in the metal because the recoil energy is too low to create Frankel defects, which is the displacement of an atom from its lattice position to an interstitial site, creating a vacancy at the original site. There are 3 different models that explain how helium-3 migrates in metals. The first picture represents the migration of helium by jumps between interstitial sites. This is similar to hydrogen in metals. Because of the large binding energy between helium atoms and other defects, this type of diffusion is only able to occur in regions without defects. The second picture shows the migration of helium using the vacancy mechanism, where the helium atom changes places with the vacancy. The third shows the migration of helium using dissociation from a helium vacancy complex and subsequent interstitial diffusion. In most simulation experiments, helium atoms and vacancies are produced and both contribute to bubble nucleation and growth. However, helium bubbles produced from tritium decay are formed without vacancies. In this situation, most of the helium atoms are formed in interstitial positions. Helium atoms then migrate using the first diffusion process, using low migration energy until a cluster is formed, or they are trapped at defects and impurities. If the helium clusters accumulate to a critical amount, theoretically 5 to 7, energy can be gained by the spontaneous formation of a Frankel pair by ejecting neighboring atoms from their lattice sites. This process is called loop punching and creates self-interstitials by pushing atoms from the metal lattice into interstitial sites. The vacancy is then occupied by the helium, and the self-interstitial atom emission process is continued as more helium is absorbed by the vacancies. This can only occur when the pressure inside the helium bubble exceeds a threshold value, which depends on surface tension in the metal, the radius of the bubble, and the atomic volume. When the bubble reaches a certain size, the energy which which must be greater than the energy binding the neighboring atoms to the bubble, for punching out of the dislocation loops is more favorable. After the first interstitial is punched out, additional helium atoms will then become trapped at the bubble, eventually resulting in an increase in pressure and growth. Here at the arrows are the examples of helium bubbles. So in summary, there are 3 isotopes of hydrogen, tritium being the only radioactive one. All 3 isotopes behave the same with respect to hydrogen-induced damage, which includes blisters, cracking from precipitation, attack, cracking from hydrides, and embrittlement. As tritium undergoes beta decay, helium-3 is formed, which can also result in damage to material by bubble nucleation and growth. Hydrogen damage can be mitigated given the right environment and the right material. This concludes my presentation today. My name is Emily Moody, and thank you for your time.